Dear learners, welcome to the next session of Physical Pharmaceutics. In this session, we will observe one of the two important characteristics that every component possesses, and the two important characteristics are vapor pressure and mole fraction. Before dealing with vapor pressure, I would like to highlight one concept called as thermodynamic systems. The reason behind focusing on this point is what? That every component that makes your system has some amount of heat and energy exchange involved within themselves. So we need to understand that when you are dealing with a system, when you are dealing with any kind of collection of matter, then there is exchange of heat or energy or mass from system to surrounding. And when all of the exchanges of energy that takes place within matter or in between matter and surrounding, that is known as thermodynamic systems. So as to understand this one, let me introduce you to the concept called as system. Now what is a system? System is the particular matter, or it is a collection of matter. So when you are focusing on the system is made up of number of components. Here we will say that that particular component is named as matter. So this matter is borderlined by the wall. In the diagram you will observe that your system is borderlined by black border. This borderline is the wall which allows or which defines permeability of heat, mass, your component or energy, which is either diffused from your border or that is accepted from the surrounding. So this borderline will define permeability, and it is thus responsible to separate your system from surrounding. So your system is overall led by your surrounding, while everything that is not included in the system, so anything that is not part of the system, is known as surrounding. So when you are dealing with system and surrounding, both make up your universe. Actually, there are three different types of systems in thermodynamics, and that systems are known as open system, closed system, and isolated system. In this case, when you are observing the exchange of energy and mass between system and surrounding, in your display you are having two arrows, two reversible arrows. One is your energy, that is red colored, and blue colored is your mass. When there is exchange of energy and mass between your system and surrounding, then that is known as open system. Then the next one, which excludes your mass. So a system on the other hand which allows only exchange of energy with its surrounding is called as closed system. And when neither your mass nor energy is exchanged between surrounding or with its surrounding, then the systems are known as isolated system. So, the borderline is responsible to define this permeability. So, on the summarized case, open systems allows exchange of energy and mass, closed systems allows only energy, it won't allow mass to permeate, and in case of isolated system, you cannot exchange either mass or energy with its surroundings. The next case that we need to understand is vapor pressure. The pressure exerted by the gas in equilibrium with solid or liquid in a closed container at a given temperature is called as vapor pressure. So the vapor pressure differentiates from partial pressure in the manner that it is in the closed container, the pressure exerted by the gas at a given temperature. So this vapor pressure is a liquid property related to evaporation. And so as to understand this concept, let me take you to the system. Here you are having open system. So the white bordered box is your borderline, which segregates your dark gray colored surrounding from light gray colored system. Now here, right now you are having constant temperature. So every component which makes your system, for example, you are dealing with the water, you are trying to boil that water, and so as to boil that water, you are pouring that water into a container, and then you are keeping that container full of your water on the gas. So here your system is made up of your gas, your container, and water itself. So in the open system, now you are having water molecule. Now every molecule has its own kinetic energy, and that kinetic energy is related to the temperature of the system. Now as I am applying temperature to the system, this liquid will get converted into, there will be transformation of phase. So your liquid water will get converted into water vapors. Now how it actually takes place? Let's see. Here you are having open system. Now to the open system you are supplying some amount of heat. So obviously at a defined temperature your system was stable. Every component, those were having their own kinetic energies, they were stable. But as now you are applying temperature, the kinetic energy or distribution of kinetic energy will takes place. And this distribution of to some few molecules, because of this distribution these few molecules will have some amount of kinetic energy. They will gain that kinetic energy which will overcome the attractive potential energy. Here the intermolecular forces are your attractive potential energy, and because of this, as the kinetic energy of few molecule overcomes the attractive potential energy, they will escape into the gaseous phase from the liquid phase. So here you are observing some bubbles, and they are nothing but your representative of vapors. So here in this system initially you was not having any kind of water vapor surrounded in your system, but as you are applying temperature your water is now converted into vapor, and in your open system you are, as you are supplying the temperature, what will happen? The water will undergo conversion into its vapor form, and that is only because of overcoming of the kinetic energy by the means of temperature. Now actually what happens, as this system is your open system, these molecules will diffuse into the surroundings and systemically into atmosphere, which eventually leads to convert your liquid into its vapor, and we are referring this case as evaporation. Whereas if I am closing the system, now see here you were not having any kind of lid, the system was open, but right now here you are having a closed system. Now what happens, as you are supplying temperature there is continuous change in kinetic energy, but in case of closed system the molecules which evaporates will diffuse around in the gaseous space. But remember, the diffusion is within that surrounding only. Means because of the closed system, that gas will not eventually diffuse across your membrane. So there will be the only energy. Mass will not transfer through the boundary line. So these vapors or these material in gaseous phase will systemically collide with the liquid, and the kinetic energy of the gas molecule has the same distribution as the liquid molecule. So at this point in closed system the kinetic energy of gas molecule and kinetic energy of liquid molecules at that particular same temperature will get distribute equally, and because of this the component which is covered into your surrounding, which is distributed into your system, will stick to the liquid. And here you will observe that in a closed container Both the evaporating and condensing means conversion of your vapor into gas and conversion of your liquid into gas and conversion of gas into vapor. So here in case of closed system you will have evaporation first, which allows overcoming of kinetic energy and thus that increases escaping tendency of your molecule, and in the same way it will lead to condensation, which has the impact of the kinetic energy of both of them will become equal. Now here one important thing that need to understand is that while all liquids have same vapor pressure, though you are dealing with open system or you are dealing with a closed system, the vapor pressure is a strong function of temperature. Till now, we have seen that whatever impact is by the application of temperature. As you are applying temperature, it will result into change in kinetic energy, and that change in kinetic energy in some liquid have a significant vapor pressure at room temperature while others do not. Now in some cases, some liquids which are having substantial vapor pressure at room temperature, to them we are referring as a volatile materials. Might be they won't require some amount of additional energy. They will neither, they are not going to exchange energy or they are not going to exchange mass. They will directly get converted from your liquid phase to gaseous phase, and to them we are referring as a volatile material. It means that they are having rapid evaporation rate. Now the next property that we need to focus on is your mole fraction. Now, what is meant by mole fraction? The mole fraction of compound is nothing but the simplest another measure of your concentration. You are going to measure concentration in terms of mole fraction. So it is simply the number of moles of a particular substance compared to the total number of moles. So as it is a total value, the mole fraction of substance always ranges between 0 to 1. So the number of mole of one substance in a mixture can never be more than the total number of moles. Means I am having mixture composed of N1 and N2 number of moles. So the mole fraction will become N1 divided by N1 plus N2, and the mole fraction is given by symbol X. So if your system composed of number of moles as 2, then the mole fraction of system will become the ratio of number of mole of individual to the number of mole of combination. Here in this formula, N1 is the number of mole of component and N1 and N2 in the combination is the total number of moles of all the substances in the mixture. When we are dealing with the partial pressure in a gas mixture, it is important to consider only moles of the substances that are in the gaseous phase, as these are the only ones that contribute to the pressure. When the relationship between these two, that is your mole fraction and vapor pressure, is under consideration with the application of temperature, then the vapor pressure and boiling point both are related to each other. And so as to relate them, the diagram which represents the relationship between vapor pressure, boiling point and mole fraction is called as boiling point diagram. Before moving toward boiling point diagram, let me ask you what is meant by boiling point. For what temperature you are referring it as a boiling point? Yes, you are correct. The temperature at which the vapor pressure is equal to 1 atmospheric pressure, that temperature is known as boiling point. Thus, you can say that the trend in boiling point with intermolecular force is related to the trend of vapor pressure with intermolecular force. Means the relationship between vapor pressure and boiling point, you can say that high intermolecular force, because of the high intermolecular force, it will be difficult for the gaseous phase to get into the gaseous phase. So this equates low vapor pressure with high boiling point. So as the compound has lower vapor pressure, it will require more amount of temperature to match with the 1 atmospheric pressure. So obviously the amount of temperature supplied so as to match with 1 atmospheric pressure will be the more, so lower vapor pressure will result into high boiling point. And considering this relationship, so as to draw boiling point diagram, we will have two coordinates. One is for your temperature and second one is for your mole fraction. Now suppose I am having two components. Okay, now here, as I am having two components A and B, as I am dealing with mole fraction here, so initially one will have 0 mole fraction, whereas second one will have highest one, and vice versa. When it has 0, it will have highest one. So now at the start, when I am dealing with the component A, so in the case when I am transforming the mole fraction of A from 0 to 1, so the vapor pressure will be at this point, this one. So when I am supplying temperature, okay, as I am supplying temperature, what will happen? Along with temperature, so as to boil that liquid, your vapor pressure will start to increase. So as to match that 1 atmospheric pressure, if this is your 1 atmospheric pressure, then so as to match with this 1 atmospheric pressure, suppose this is your 1 atmospheric pressure, and so as to match with this 1 atmospheric pressure, what you need to do? You need to supply maximum amount of energy. So the change so as to match with 1 atmospheric pressure will be from lower to higher node. And systematically, as you are lowering the temperature, you will find this as a fall down curve. So this has been represented by the means of boiling point diagram. Here the pink line shows you that change in vapor pressure, that is your vaporization, whereas fall down will result into your condensation. So vapor composition will be there, and to the fall down you will have liquid composition. So this was about vapor pressure and mole fraction. Thank you.